Hello, how are y'all doing today? Well, I would love it if one of you would unmute so I can verify that I can hear you fine.
We're good. How are you?
I appreciate that. Super good. So that's wonderful. And let's think. Just I want to sort of start by doing a share screen and then we'll move forward like normal. And starting, I guess, with things that are related to administrative. Okay. First off, I guess we've got an exam coming up. Let's verify that we know when that is. At least I should verify that I know when that is. I think I've got it all set up here, but essentially, tomorrow in class, we should be going over review questions that are online. And then sort of the exam will be sort of released into the wild, if you will. So shortly following class, like at 1 o'clock or 1:10 is when the exam becomes live, and you've got until well 2 days plus then until 11:59 p.m. So I guess that's Friday for y'all. You have until Friday to get it finished up. Do want to draw your attention to there was homework due yesterday, but I haven't yet put the answers online, and I want to do that right following class so you could review that before then your test hits. Also, problems that are due tomorrow, due Wednesday. I guess I should by Thursday morning have the answers available to y'all, and that might be helpful as a way of prepping for then the exam. Okay, so I guess tomorrow there's a lot of Q&A to make sure you feel comfortable with the material before you open up the test. The test is going to be, I think, 55 minutes or something like that, and so I figured that's a 50-minute exam, plus 5 minutes for you to collect any screenshots you may have taken, or if you did something on paper and took a picture of that, and then sort of put that into a file. 5 minutes to sort of upload anything in one PDF, anything that you would really want me to be able to see. So if you're doing a question, you're working away and you're thinking, well, I really want to make sure that I get partial credit. So I'm going to sort of show the way that I got to my answer. That's something you should demonstrate. Okay. It will be largely, are you right? And if you're not right, sometimes showing me the way you got to your answer can help me identify what sort of error you had been making. It might be small, in which case, pretty good partial credit. Or if it's a huge error, a conceptual error, well, then that's a little bit tougher, but still, it's better to show me how you got to your answer than to not show me at all. And all of a sudden it becomes a zero score. Don't do that. What else? We're going to talk about today in class the one last topic for the exam. It's chapter 3, general linear models. The content for the exam is the review stuff that you know from the t-test, from that past class, ANOVA that you saw most of, if not all of, in your past class, and then regression. Again, you saw most of that in your past class. So it's a lot of the past plus today's content for the exam. I think that's it in terms of things I wanted to be sure to say to y'all, but I might have not answered your question. So if you got a question, now's a good time to ask it, especially if it's administrative in its nature. Okay, so I'm going to go with I didn't hear a question yet. Feel free to always unmute and then just tell me the question. What about subject matter questions from regression? How about subject matter questions on anything so far as you're prepping for your exam? Oh my gosh, exam in week, like Wednesday of week 2? What the heck is this? Accelerated pace? Yeah, 4 days a week. It's a bit more than the normal class. 4 days a week, an hour a day in class and an hour a day of lab type content. Plus, then on top of that homework, it is a beast. but I have to say it's better than a university where I taught on the East Coast at one point in time. They had concentration camp calculus where they did an entire year's worth of calculus in 12 weeks. So 2.5 times the pace. It was 3 hours of class every day. Students would go home and do 3 hours worth of homework and then do 2 hours worth of studying to prep for the next day's class. Repeat that for 12 weeks. It was hard to pass, but the people who did real well, the people in Stat 313 who do real well in a summer, they know the material really quite well. One of the past Stat 313 people went on to sort of get a bachelor's degree in statistics. The class 3 years ago worked out so well that they said, you know what, sign me up for this. They did quite well overall. In fact, enrolling in the master's degree program and got the master's as well. Okay, last chance for questions. I've been stalling yet again, stalling. Okay, so let's move forward then in the material. And always, please feel free to just interrupt if you would like to, because the question comes to mind that you had forgotten to ask, or something I say sparks your understanding or lack of understanding, and you want to get it clarified before we move forward. That's always a good idea. So maybe what I'm going to do is actually put that up there so we have some blank canvas to work with if need be. And I'm going to start in on chapter 3 by simply saying chapter 3 is a conceptual bridge between everything we've done in the past and saying, yeah, it's all the same. And that will allow us to go further in the near future. Literally everything we've done so far in ANOVA or a regression or even a t-test could be thought of as one of these things called a general linear model, or if you will, some sort of a regression problem. You remember that the regression word equation that we had is y equals x. Y on the left-hand side, the response variable equals x, our quantitative explanatory variable, or we said y is x, it could be categorical. And heck, if there were even two different levels, y equals x, that word equation basically says, flowers equals sex on the trees, that the number of flowers depends on the sex. And ultimately, what we're going to end up with is a situation where we'd say a response variable is equal to, it's a prediction method, an intercept plus a sum of coefficients times x variable values. So even if it's analysis of variance, we could really write that out as there is an x, and then it is multiplied by nominally a slope. I won't call them that in this chapter, but essentially it's the mathematical equivalent of a slope. You know how you could write an equation of a line in a point slope format? You could also tell me the two intercepts, the x and the y intercept, and it's the same thing. There are a lot of ways of telling me the equation of a straight line. There's a lot of ways of writing out your conceptual model, and if they're algebraically equivalent, they are the same. And the thing we want to really emphasize in this chapter is, yeah, your y variable has to be quantitative. We will deal with that on the second to last day. What if your response variable is not quantitative but categorical? We'll deal with that later. But your x variable, so far we have quantitative regression, categorical analysis of variance, or both. And today we're going to sort of put this categorical explanatory variable on its head, and we're going to say there's a better way of thinking it through. Our old way of life said your y, on average, is based on what group you're from. So literally our equation here, the top equation, and let's make sure I got a good color. Okay, red's a good color. Our equation basically says y is a function of what mean it is. What group mean, plus there's how far above your average for your group you are. So this epsilon ij that says compared to your group, where are you at? And mu is the mean of the group you're from. All we're doing today is we're saying that mu I could be written as mu plus alpha I. Okay, so the mean of the ith group is some sort of a reference mean plus the effect of being in group I on that mean. So you could think of that as, well, maybe there is formally a reference group. Yeah, literally, we might want to, in the discrimination against the handicapped data set, we might want to say no handicap at all. That is the reference group. And alpha I could then correspond to how much does a person's average go up based on which handicap they're in, or if alpha is negative, it says your mean of your group will go down compared to the no apparent handicap group. So these alphas, that's how we're going to choose to phrase things moving forward. These alphas, if you will, are the effects, the effect of being on, or the effect of being in a group. So effect, EFFECT, the effect has an effect. Okay. So literally, what is the size of the difference between your group and then that reference group? Now, I want to sort of just note something that is a little on the awkward side. We don't really know the value for mu. There is no mu in some contexts. I guess if there is a reference group, you want to compare to that natural reference group, but what if there is no natural reference group? We still have to have a point of reference. And this is where, if it was a regular term, I would probably have y'all stand up and say, oh, look, you are sort of tall over there in the back. If you were the reference point in terms of the height of an individual, every individual has a height, okay? And it's going to be compared to your height. The alpha would correspond to a person who is below average, and alpha is how far below the height of the tallest person it is. And then I'd ask this shorter person who's often sitting closer to the front. And from your point of view, are we largely taller? And would you say that the alpha from your point of view is positive, that for each of us, and I point around the room like that guy over there, yeah, he's how much taller? Oh, 8 inches taller? Yeah, from your point of view, the effect of being him versus you is a +8. And then I have to point at the tall guy and say the effect of being her instead of you is a -8. So there are different places that we could refer to. The reference is going to be different. But whatever the reference is, whatever my reference point is, my null hypothesis that we had expressed earlier as all of the population means are the same, group 1, 2, 3, 4, 5, all are the same. We're now going to say that a slightly different way. The effect of being in a group on then the mean is 0. Let's think that through. If we're comparing this discrimination against the handicap data set, if we're comparing to the no apparent handicap group, if the difference of the hearing loss group and the no apparent handicap group is 0, okay, mu h is mu n plus 0, you'd say the effect of hearing loss is 0, okay? If you want to say that all of the effects are 0, it says that there is no effect of treatment. It's almost like the slope being 0 in a regression. There is no trend. If all of the effects are 0, there is no impact of which group you're in on the average. Okay, so any questions about that? So I'm just going to go ahead and do this. And algebraically, I'm going to sort of show you GMP has one style, but there is a slightly different style instead that I could utilize. And then the lab sort of reinforces this. So let me go with, I'm going to go with shoot, I want to make sure I don't overstep my lab. So hold on a second. Hey, I think I know how to do that more quickly. Just want to verify that I'm not showing you the same stuff that you're going to be redoing, or I should say doing in the lab activity. So in the lab activity, Got that data set. And then, okay, perfect. So I'm going to use the discrimination against the handicap data set. And that makes a lot of sense to me for this lecture. So, mhm. Discrimination. Nope, 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 nope. Wrong data set. There we go. Okay, come on. So here we have our data like before. You've seen these data previously. And let's just do that. Under Graph Builder, I'm just going to typically walk you through things the way I would if I were a researcher here. I'd say, how does the score or does the score depend on which handicap group you're in? And it looks as though some of the groups, like the crutch group, have a higher mean than the other groups, like the hearing loss group. It looks as though this group seems to be a bit of a difference. So maybe there's a difference across the means. But let's rephrase that. Is there an effect of which group you're in on the mean? That's really the thing we would tackle, not with Graph Builder, but with a formal analysis. Fit Y by X is your friend. We learned earlier that we could say score doesn't depend on the handicap. Is there a difference in the average scores across the groups? I would just click give me my ANOVA analysis of variance, ANOVA. You'd say with a p-value of 0.0301, you'd say there is a noticeable difference across the groups. Not all of the means are the same. We're now going to switch gears and do this a little bit differently. Instead of analyze fit y by x, we're going to analyze fit model. That's the real difference is if we're at chapter 3 or later, almost invariably you're going to be using analyze fit model instead of analyze fit y by x because there may be other things we could put in the model, but for now we're going to start small. Yeah, literally, I still say, does the score depend on the handicap? It reads about the same as fit y by x. I click run. And I see output that, well, it looks slightly different. It gives me that graph, which I hadn't seen before. It gives me this other thing, which I don't really love. It doesn't show me necessarily a picture, but I am looking at some things that are pretty familiar. If we liked regression, you talk about R squared as what percent of the variability and Y could be considered explained by the X's, about 15, and it's 15. Our ANOVA for the model as a whole has an F value of 2.86, just like before, a P value of 0.0301, just like before. And this thing called an effects test is also an F value of 2.86 and a P value of 0.0301. So I'm thinking this looks about right. It looks as though we're fitting the same model. So what's different? What's different is now we can talk about the effect of being in one group on the mean. And if I click on this parameter estimates, we earlier had seen an intercept and a slope. Now here we've got what looks like an intercept and an effect of it being an amputee on then the average. The estimated effect of it being crutches on the average is to raise the score. The amputees is to lower the score. The effect of hearing loss is to lower the score by 0.88 units. The effect of no apparent handicap is to drop the score by 0.03. And I'm saying, hold on, there's 5 groups. There's amputee, crutch, hearing loss, no apparent handicap, and W for wheelchair. We are not seeing the wheelchair group listed at all. Here's just the way statisticians think. The people who write software and statisticians in general are saying, if you've got 1, 2, 3 of 4 effects, how much is this group different from some reference? Maybe the 5th one is predetermined. Yeah, literally, if you have 4 degrees of freedom for the model across 4 estimated parameters, we could tell you completely how different the groups are from each other. Our software goes with a sum to 0, or the average effect is 0 styling. So yeah, literally here, I'll tell you this negative 0.05, 0.99, a negative 0.88, a negative 0.03, the sum of those one, two, three, four terms plus the missing fifth term, the sum would have to equal zero. So let's go ahead and I'll see if I could do the math. Probably not in my head, but I'm hoping that one of you could be helpful for me. So at negative 0.05 or 0.50, and I'm going to round a little bit, plus a 0.99. The effect of it being amputee and crutches, hearing loss is a negative 0.88. I'm doing a little bit of rounding. And then I've got a, for the no apparent handicap, plus a negative 0.03. Again, some rounding has been achieved or utilized. What is that sum? I think I could probably
Negative
do it.
0.42.
I'm sorry, what?
Negative 0.42.
So negative 0.42. Thank you. Negative 0.42. So if I have five numbers that sum together to zero, and the sum of the first four of them is negative 0.42, doesn't that mean the fifth one would be a positive 0.42? It's got to be. It's got to be. So inside GMP, we can literally say, you know what? I don't want to look at just the first four. The software designers say the first four are necessary to show to you. We've got 4 degrees of freedom. I'm only going to show you four terms. But if you want to see the fifth term, under estimates, you literally could say expand those out. Show me all of the estimated values. The expanded estimates gives us our last term here, our negative zero point 0.5, like before, our 0.99, like before, the negative 0.88, like before, the 0.03, like before. And then the last one is a positive 0.41. I'm thinking that's rounding error that we had when I wrote that down, okay, that caused the bit of the hiccup. So what we have here is sort of a confirmation that the sum of all five terms is zero. We tend to show only the first four of the five when we're using JMP's sum to zero parameterization. And I'm going to just write that down, sum to zero. Because if the average of them is zero, they sum to zero, those effects. That's just JMP style. That's the style that statisticians in general prefer. However, there are some contexts where you want to compare to a particular group, a reference group. You might want to compare to the first group alphabetically or the last one alphabetically, or you might have no apparent handicap as your preference. You might want to refer to that as your reference group. How could we pull that off? Well, I'm sort of thinking if you give me those group means, I could then do it. Let's go ahead and try those group means. I'm going to turn on under Analyze, Fit Y by X. I'm going to say, how does the score differ across the handicap groups? I've got my graph, and I'm just going to display the means. I don't need the whole ANOVA here to get these averages. And if my natural reference group is no apparent handicap, that says 4.9 is what I want to conform to or compare to. The amputee effect, and I'll call that alpha hat for amputee. That's going to be just the the Y bar for the amputee group minus Y bar for the no apparent handicap group. In my case here, I've got 4.43. Again, I'm rounding it 2 digits past the decimal mark, and that's sort of a problem sometimes, 4.90. And I'm thinking that's a negative 0.47. Please correct me if I'm wrong mathematically. That's easy for me to get it wrong. My claim is, though, it's a negative 0.47. We're comparing to a negative 0.47. I know we're comparing to the no apparent handicap group. So the amputee effect, the difference between the amputee mean and the no apparent handicap mean is, well, the amputee group is 0.47 below. So let's go ahead and see how we could verify that with our data. I'm gonna delete this here. I'll recreate it when need be. Man, shoot, I'm sort of bummed about this. I like it to be clean and easy and not overlapping. Oh, I know what I could do. I could erase everyone in sight. Okay, you might have noticed, probably not, but you might have noticed under estimates, we did turn on the expanded estimates. There's this other thing called indicator parameterization estimates. That's what will allow you to compare to a reference group. So I'm going to turn that on. So my indicator parameterization estimates say, well, there is an intercept. It's a little bit different from before, but the amputee effect is a negative 0.91, and that's different than before. Rather than comparing to some random reference point, we're comparing to, well, a different and possibly random reference point. Crutch group is a 0.58, a negative 1.2. What are we comparing to? What we're comparing to is the group that was left off. Let's go ahead and again display those means under analyze my fit y by x. I'm going to sort of display the averages for each of these different groups, means and standard deviations. Notice here that the wheelchair group clocks in at a 5.34. That is the average of the wheelchair group. That is now our indicator parameterization reference point. The intercept corresponds to the reference point. The reference group here is the wheelchair group. And I'm saying the amputee is 0.91 below the wheelchair group. The crutch group is 0.58 above the wheelchair group. Crutch at 5.92 is 0.58 above the 5.34 wheelchair group. Yeah, that checks out. So we're comparing here to the reference group of wheelchair, and some of you are thinking, you said, dude, that you wanted to compare to no apparent handicap. You're comparing everyone to the wheelchair group. Yeah, we are. We should be able to fix that, however. The solution is this. If you turn on the indicator parameterization, and the group that's left out is not the group you want to be your comparison group, the reference group, you could reset the reference. The way to do this, and this is walked through slowly in the lab, the way to do it is to right click on the column and say under column properties, value order. So this is something where, yeah, it's sort of hard to remember to do. And so that's why it's good that it's built in the lab. But you might want to write down, right click on the column, then column properties, and then value order. That allows you to say, which group do I want to be the reference group? Choose the reference group, and then that will be your last group. We're given then for handicap, the one that's listed last, that's the reference. I want no apparent handicap to be the reference group. I want to put it in the last slot. Notice the slot is highlighted here. Yeah, no, last slot is indeed going to be your reference group. Period. I click OK. We've reset now the reference group. If I were to do my analysis over again, analyze fit model as before, how does the score depend upon the handicap? I'm now going to compare to that reference group of the no apparent handicap. And we don't see that indicator parameterization immediately. What we see is the old-fashioned way of doing it. My regular parameter estimates are just like before. It's comparing to some number that we haven't talked about just yet. How do we compare to the reference group? Just because we don't see none or no apparent handicap listed doesn't mean this is a reference group. You literally need to say, I want under estimates to turn on the indicator parameterization. My indicator parameterization, only look there. You will find your reference group is the one that's missing over here, and no apparent handicap is indeed the one that's missing. So like what we saw before with our means, the no apparent handicap group has a 4.9 as its mean. That is the intercept. That's the comparison. And where does no apparent handicap compare to the 4.9, it's right at that mean. So the effect of the reference group is literally zero. The effect of it being an amputation is a negative 0.47, or if you will, 4.42 is 0.47 below the reference group's mean of 4.9. That's the math that we had done earlier. Yay. Okay, so we're happy here. We've got these two different way of doing things. This parameter estimates, the indicator parameterization estimates, where that's a little bit cleaner because we're comparing to an actual group. What is this parameter estimates comparing to? What is this intercept even equal to? The way I like to think about it is, what if I told you there's a person in this study and you want to know about estimating that person's score, the score they gave out. And I'm not going to tell you which group they were in. You don't know which videotape they watched. You don't know which of the 5 videotapes they watched, but you believe they're equally likely to have seen any of the 5. Wouldn't you want to just take the average of the group averages as your reference? Indeed, that's the case. If we don't have things where we want to have a group to refer to, we're going to use this sum to zero parameterization. And in the sum to zero styling, okay, in sum to zero, our mu hat, okay, that's the number to which we compare. We're literally going to say that that is 1 over k, because there's k different groups out there, times the sum of y bar for group k. So if I take my 1, 2, 3, 4, 5 different group means and add them up, divide through by 5, that's the average of the group means. That is the sum to zero style. Now, some of you might say, well, isn't that just the average of all of the data points? Indeed, it will be in the situation where we have an equal number of data points per group. And now is where I wish I hadn't shut all the GMP things down. Maybe they're still open, but just hiding. Okay. Let me do this. There we go. Okay. I seem to have put it over here. Okay. There we go. If you literally want to show a description of what's going on, under Analyze, let's just go with, I'm going to make a graph with Graph Builder. I'm going to plot the actual individual scores along the y-axis, and the handicap group will go along the x-axis. And I'm just going to click OK, and then maybe I'll be able to turn on something under Graph Options. I might be able to show, not so easily. Darn it. Okay, I'm going to have to do this another way. Okay, so moving off to the side. Inside JMP, there's always a way to do the thing, whatever the thing is that you want to do. Sometimes it's going to be via a different set of pathways than you would immediately think. I just want to make a graph here, and I'm going to use Analyze Fit by Y to make the graph I want because it's easier to get it quickly. If I have the score shown here and the handicap shown along the x-axis, the first thing we get is the graph I sort of wanted to show you. And if I turn on under display option, those mean lines, we had done this before, where we said the green group means, and then the grand mean is shown here in gray. In this case, because we have an equal number of data points per group, how far a group mean is away from the grand mean corresponds to that alpha hat. So alpha hat for group crutches, here's alpha hat. For group amputee, alpha hat. For group hearing loss, and alpha hat for none. And then finally, alpha hat for the hearing loss, or that's none, hearing loss. There we go. I reordered them, so it put them in a different order. My different alpha hats correspond to comparing to the different means. How far is that green mean above the average of the averages? But if we were to consider a different situation where we have more data points in one group, Then in another group, and I'm thinking like the dioecious trees where we had like 60% female trees and 40% male trees. If I'm going to choose a reference point, what would we want the reference point to be? And the lab will walk you through this, but the reference point could be the female tree average. The reference point could be the male tree average. Second possible reference point. A third possible reference point could be, and this is the one we recommend, the average of those two averages. And that's sort of like walking through the forest and saying, I'm going to collect another tree. I'm not going to tell you whether male or female tree is the sort of tree that I'm going to grab and measure, but I'm going to count the number of flowers. And if you think it's equally likely that the next tree will be an M versus an F, you would take the average of those two averages for getting your estimate of mu hat, your reference group. Mu hat corresponds to the number you'd bet on for Y if you had no information about which group you're in. The sum to zero parameterization really nicely corresponds to you don't know which group you're in, but you know you're in one of them and you're equally likely to be from any of those groups. I think there is. Oh, yeah, that's sort of a cute little thing. Uh, we literally could write out ANOVA as a regression model with multiple x's. Literally, if x is a 1, 0 value, sometimes called an indicator variable or a dummy variable, and I want to show you this now. If I have 1, 0 variable values, they either indicate which group you're in or not in. So like for this 15th data point, its value for amputee is 1, and that means it's an amputee. But if the value for crutch is 0, it means, well, the group is not the crutch group. And if it's not the hearing loss group and not the no apparent handicap group, but it is in the amputee group, you know which group you're in. And so I guess if you're in the no apparent handicap group, you know your no apparent handicap effect is 0. Similarly, crutch will have a value of 1 when it's someone in the crutch group. If your hearing variable is a value of 1, you have a hearing aid. If, however, across all of the values for your 1, 2, 3, 4 dummy variables, if they're all 0, you're not in the amputee group, you're not in the crutch group, you're not in the hearing loss group, you're not in the no apparent handicap group. That means you must be in the wheelchair group. So if I were to run a regression with these x as x variables, I should be able to fit the model quite nicely. And let's go ahead and try that. We're using a method that's a little bit different than we're comfortable with so far because we haven't dealt with multiple regression. But the score does depend on whether you're an amputee or not, a crutch or not, hearing loss or not, no apparent handicap or not. I'm claiming that the score depends on these 1, 2, 3, 4 things. And you're saying, well, that depends on which group you're from. This is just another way of characterizing that. And we could run that analysis and we get a lot of output. Let me grab it and drag it over here so you can see the output nicely. It does look as though same 15% R squared, same F ratio, same p-value 0.0301, and my parameter estimates are basically amputee or not compared to the wheelchair group, crutch or not compared to the wheelchair group, hearing loss or not compared to the wheelchair group. Literally, the only way to have an increase in the hearing variable to go from a 0 to a 1 in this data set is if we were in the hearing loss group and all of a sudden switch over into, let me say that again more correctly. The only way to have a change into the hearing loss group where we would have a negative 1.29 impact, that being the slope of a 1 unit increase in hearing. The only way to get a 1 unit increase in hearing with no other changes at all, no changes in the amputee, crutch, or no status, is to go from the wheelchair group into the hearing loss group. We were at 0 for all of the values, and then all of a sudden we go into the hearing loss group is a 1, and we subtract 1.29 from my wheelchair group intercept average, if you will. So the wheelchair hearing loss is 1.29 below the wheelchair average. Okay. So there's a lot of different ways of viewing these general linear models. The upshot that we're trying to convey to you today is really only this. There's a lot of ways of saying the group you're in has an impact on the response variable. And literally, the point of reference is really huge. We usually go with a sum to zero parameterization, but frankly, I could go with other styles. The other styles are just as good. So between the lab today, which is due by tomorrow's class time, and then the homework assignment, which is attached to today, it's the antibiotics data set is corresponding to today. You should have a good idea, but I'm recommending strong recommendation that come to class tomorrow if you've got any questions on chapter 3 content before we sort of go over review problems. There will be some reasonable time for questions, and questions on chapter 3 are great before taking the exam. So I always talk way too quickly and maybe way too much. I want to stop and pause. Do any of you have questions before we call it a day and you guys go poke at your labs? Okay, what I'm going to do is stop the share. And if you have any questions, we still have the opportunity to tackle them. Otherwise, I'm going to stop the recording and we'll see you all in the near future, like 23 hours and 10 minutes. Okay, well, we'll see you soon. I'm going to stop the recording. Bye-bye.